Hello everyone, my name is Arudi Yuda. Today I'm going to present my paper with the title Scalable and Fast Lazy Persistency on GPUs. Now let's take a look at the introduction. Graphics processing units is increasingly used in high-performance computing, which requires a large memory capacity. However, DRAM scaling is facing difficulties. Non-volatile memory (NVM) has stepped in to provide the higher density and better scaling potential for the future main memory. Furthermore, NVM can host data persistently across crashes and reboots. Lastly, crash-consistent data, however, requires persistency models, which define when the store reaches the NVM or it become durable. In summary, the main contribution of this paper is first, we identify the design space for mapping LP on GPUs. Secondly, we show the design space exploration based on hash table choice, the use of logs versus logs free, and the use of sequential versus parallel reductions. Third, we propose the hash-table solution by leveraging the thread block as the LP region, resulting on a negligible performance overhead. Lastly, we propose a directive-based programming language support to achieve LP on GPU with low programming complexity. Now, uh, why do we need a crash recoverability in GPU? The reason is high-performance computing application can take weeks to complete the computation. Let's say training of the neural network can take weeks. Secondly, when in the middle of the computation, the system crashes and there is no mechanism to provide a crash recoverable so that the GPU needs to recompute that computation from the beginning and resulting on energy, time and resources waste. Therefore, it is an important thing to have a mechanism to allow GPUs to continue the execution after system crash without restarting from the beginning of the computation. Now, in this work, we choose the lazy persistency. Why do we choose the lazy persistency? There are reasons for this. First, that on the surface, the lazy persistency achieve negligible overheads on the CPUs. Secondly, the lazy persistency produce small write amplification in CPUs, which is a good candidate for GPU because GPU is bandwidth sensitive. Lastly, is that it does not require any persistency instruction, therefore it can be used on the current GPUs in the market. Now let's take a look at the background of the lazy persistency that Muhammad et al. 2018 defined. So here is the figure. In lazy persistency, the programmers requires to define the persistent region. This is the example. So this is uh, the store of the application, the store instruction of the application. The programmer will divide the store to several region that is associative, and then uh, its region is protected by a checksum. Here is so first you set the region, and then every region it needs to compute a checksum that will be used to protect the region. uh, Other than that, only in the last store to the same address in this case is store A, only the last store A that is contribute to the checksum calculation. And the checksum is also stored uh, in a data structure. Now let's take a look at the difference between CPU and GPU architecture. CPU uh, only have a few cores, while GPU can have thousands of cores, but it's more simpler than the CPU. And CPU is latency sensitive, while GPU is not. Uh, well, the GPU is bandwidth sensitive. In Typically in today's system, the CPU memory bandwidth is only 50 gigabit per second, while in GPU it can typically 500 gigabit per second or more. Now, the CUDA programming model in NVIDIA GPU, uh, it using the CUDA programming model. So there is a thread hierarchy in this programming model. So this is thread. Several threads will form 32 threads will form a warp, and other than that, several threads will also perform a block, and then in uh, several block several blocks in it will form a single grid. So there is a grid ID, block ID, and thread ID. Now, in lazy persistency, we need to define a LP region. What is a good LP region? LP regions are unit of crash recovery, and it should be associative. LP region selection must consider a good balance between checksum overhead and recovery granularity, so that the checksum computation is not the overhead of the computation is not that high, is not too high, and also uh, the recovery is not the we need to consider the recovery of the granularity, and then the simplicity of the recovery code construction. Now, after choosing the LP region, it needs to compute the checksum. So, considering the thread block will be a lazy persistency region, so that all threads in the thread block will perform checksum computation and produce a single checksum. In CPU, there are three checksum were considered: parity checksum XOR using XOR, modular checksum using uh, addition, and adder 32. Here is the illustration of the parallel reduction. In GPU, we have a shuffle down instruction. It is a register to register. It is a thread communication that is communicate between register to register directly without going down to the shared memory. Let's say there are 8 threads and every thread have a one value, and then we want to compute the checksum for all of the values. It just need to call the shuffle down fall for it will uh, read every thread will read the next for uh, neighboring thread in a single warp. This and then it doing summation, and then it call again shuffle down with the index 2 and find and so on, and finally it produces a single output, which is the checksum. With this with the parallel reduction, we can compute the checksum with the complexity only log n. Well, if we using the do it serially, we will need uh, to do a time iteration in this case. And then after calculating the checksum, we have to store the checksum into a data structure in a hash table. In CPU, we need a more scalable hash table even if it is less flexible. A GPU hash table ideally does not use pointers, is lock-free, generates few collision, scales well with the large thread counts, has low average insertion latencies, and limited worst-case insertion latencies. Because the insertion latency is in the critical path, while uh, the hash table lookup is not. And then we know other consideration is that since we are using thread block as a LP region, we know that the number of unique keys in advance. We know the number of the thread block before we launch the GPU kernel, so that the pointer-based hash table less attractive and unnecessary because we are not we don't need a dynamic hash table. And then in this work, we will compare to hash table, quadratic probing, and cuckoo hashing as the naive implementation. Here is our result for naively mapping LP from CPU to the GPU. From here, uh, uh, the the y-axis is the performance overhead, and we use the subset of the purple benchmark. The there are two type of hash table, cuckoo and quad. So in general, the cuckoo the cuckoo hash table is having higher overhead. It is 31.7%, while the quadratic probing is only 29.4%. Well, for MRI grading, uh, quadratic probing, the figure was truncated because it more than is larger than the y-axis, and it should be 218.6%. And for SAT with cuckoo hashing, it's also truncated, and it should be 232.79%. The reason is that why the MRI grading and SAT uh, uh, for quadratic and cuckoo respectively uh, beyond the scale very high, suffering from very high performance overhead, is that it use a lot of thread blocks, so that thread blocks a lot of thread blocks will insert to the hash table, and resulting in high degree of memory contention when inserting the checksum. Well, for the TMM, TPF, SPMV, Histo, CUDCP, and MRIQ, the difference of the overheads between the two mechanisms are much smaller. The reason is that the thread block is smaller, so the degree of the memory contention is also smaller. And then we hypothesis that the large overhead is came from the memory contention because of a lot of thread blocks, and then we calculate the hash table collision number. So this table confirm that MR grading and SAT is having a lot of number uh, hash table collision and translating to a high performance overhead. Other than that, we also explore the implementation of log-based and log-free hash table log-based and log-free stable. In general, uh, log-free implementation is having a much better performance, a much better performance compared to the log-based stable. And then we also explore the possibility of using serial and parallel reduction. Again, in this table, we show that in general, uh, the parallel reduction is much better than the serial for both quadratic and cuckoo. So we know that uh, log-free implementation and parallel reduction is a good choice. But however, considering these two design is we still suffering the performance overhead around 30%. Then we rethinking about the LP ranking decision. We know that the thread hierarchy in GPU borrowing model provides a natural fit to this problem for several reasons. Thread blocks are naturally associative, as GPU hardware provide no guarantee on the execution order of thread blocks, and also provide a good amount of work so that the checksum computation won't be a major overhead. And then a thread in a block can communicate with each other with on-chip shared memory. And lastly, it also simplify the recovery code. Therefore, we propose a scalable LP on CPU that leveraging the thread block ID as the one that is used to index uh, the the array that will be used to store the checksum. So that with this we are free from the rest condition, and then we our our stable solution is having a 100% load factor. Here is the illustration of our proposed solution of our optimal solution is we are using checksum global array. This is the thread block in GPU there in and then several thread block we perform a grid, and then LP region is a thread block, and so we LP region is in a thread block, and then its thread block will insert to our checksum global array with different address that indexed by the thread block ID, and we achieve a good a very low overhead. In general, it was a 2.1% overhead, uh, and then the space overhead is only 1.36%. And also, furthermore, we also propose a directive-based programming support that is making easy for programmer to implement the LP, the Lazy Persistency on GPU without much complex, without having to modify the code. Just annotate. We propose two directive pragma NVM LP CUDA init for creating the checksum global array, and pragma NVM LP CUDA checksum for performing the checksum calculation. So, in conclusion, we show that LP works well on GPU, and then we show the characterized performance over their design space, and then we identify the performance bottlenecks sources, and based on this, we propose hash stable solution. And lastly, this is the first work that provides persistency on GPU with negligible overhead, only 2.1%, and low write-on amplification, and is ready for use in today's GPUs market in the market. Any question? Thank you. Thank you. Any question?